Levers in Under 4 Minutes by Anton Sirachi-Mifsud and Vincent Susilo.
Part 1. The three key terms. To understand levers, you need to know three key terms. They are load, effort, and fulcrum. Everybody's drawing examples, so let's be creative and find some household examples. The pass to the bowl can be a load. Any piece of matter can be a load. These Sennheiser headphones can be a load because it is matter. Vince's sister can be load. She is matter. Muscle can be used as effort. The motor inside this blender can be a source of effort. If, however, you were to lift the entire blender with the motor, then it would be a load. The spoon in this example is used as a fulcrum. In summary, the three key terms are load when you're lifting, effort what powers the lift, and fulcrum is where the lever balances. Part 2. A wonderful world of levers. There are three main types of levers. They are first class levers, second class levers, and third class levers. Drawing examples are boring, so let's go find some. Me opening the Milo tin is a form of a first class lever. Why? Because the order is effort, fulcrum, load, EFL for short. This is called a force multiplier. As I open the DVD cover, I'm using a second class lever because the order is effort, load, fulcrum, EF for short. Our second class lever is also a force multiplier. Third class levers are speed multipliers because they multiply your speed. As I hold Vince's tennis racket, the order is LEF, load being the tennis ball, effort being the racket, and fulcrum being my hand. In summary, the three types of levers are first class, second class, and third class levers. First class and second class levers are force multipliers, and third class levers are speed multipliers.
Part 3. The fine print. If we're going to write up an advertisement for levers, we'd put two major points. That it's a magic machine that multiplies speed and force, and that this machine can move anything. But wait, what's all this fine print doing here? Let's go take a deeper look at it. Fine print 1. Mechanical advantage. The mechanical advantage is the advantage of a machine. That's pretty much it. So, how do we calculate it? Well, to calculate mechanical advantage, we need to divide the load, measured in kilograms, by the effort, measured in kilograms or newtons. Let's do an example. On this lever, I have 10 kilogram load with an effort of 5 kilograms. If we were to do the math, it would equal to a mechanical advantage of 2. Notice that the mechanical advantage doesn't have a proper unit of measurement. Let's move on to the second point, which is work. Work happens when an object is moved. Let's use a lever to explain this. When my sister holds down this lever, she's only using effort. Watch as she now slowly moves the lever back up. While she's moving it, she's generating work. So, how do we calculate work? To calculate work, you need to multiply force, measured in kilograms or newtons, by the distance moved, measured in meters. For example, if I had 10 kilograms of force and I used a load 10 meters, that would make my work 100 joules. Now we understand work, let's move to the third fine point, which is balancing. But levers are like equations. Just think of your fulcrum as your equal sign. Let's do an example. Let's say I have 5 kilograms of load 2 meters away from the fulcrum, and I had a 10 kilogram load 1 meter away from the fulcrum. The lever would balance. Why? Because on both sides of the fulcrum, there are two equations that both equal 10. Here's a formula to help you out. Load times distance equals load times distance. Again, think of the equal sign as the fulcrum. In summary, all you need to know is that the mechanical advantage is the advantage of the machine and can be calculated by dividing the load by the effort. Work is generated when an object moves and can be calculated by multiplying force by distance moved, and that levers are just an equation. Just think of the fulcrum as your equal sign.